Welcome to my channel Maithili SK. In this session we are going to see about single sideband suppressed carrier AM. This also completes the generation part and the deduction part of the same. So first introduction, we'll see why we go for single sideband suppressed carrier AM. Then we'll derive the mathematical representation of the same, and then we'll see the types of generations for single sideband suppressed carrier AM and deduction of the same. Finally, we'll touch with the power calculation and comparison how the power is being calculated and why this is necessary to suppress all these sidebands. So, introduction, single sideband suppressed carrier AM. Why we go for single sideband suppressed carrier AM is important. This is actually explained in the double sideband itself. We know the three carriers are present here, three components. That is, in the first case, we have suppressed the carrier and only two sidebands are transmitted in case of double sideband suppressed carrier AM. Whereas in single sideband suppressed carrier AM, we are going to suppress one of the sidebands because both the sidebands are present in the previous case. So if we suppress one of the sideband, what will be the power calculation? So we know instead of carrying two apples, if we carry one apple, the weight will be reduced. So comparatively, when you consider with respect to power instead of weight, here the power to carry the sidebands for transmission will be reduced when it is reduced or suppressed to 1. So that we are going to compress or suppress this carrier as well as the sidebands, one of the sideband. So it is called as, hence only one sideband is present. So it is called as single sideband suppressed carrier amplitude modulated signal. So based on the bandwidth, we can say with respect to the spectra, the signal present is only the sideband form. So here we know from the carrier till this we have only the FM signal. So the maximum bandwidth of a single sideband suppressed carrier modulated wave will be just FM. Next, coming to the mathematical representation of SSB-SC AM. Previously we know for a modulation, we know there are three parts we should consider. One is the carrier, another one is the message signal. So now considering the message signal here as m of t, I am going to take am cos omega mt. So omega mt here is represented here as 2 pi fmt and carrier signal is represented as ac cos 2 pi fct. So we can represent this mathematically, this equation, just by multiplying the same. So I am going to give this to a product modulator, one message signal m of t and a carrier signal c of t, just to a product modulator which will multiply these two signal and produces the output s of t, which is nothing but message into carrier. So when we are multiplying these two signal, we can say this will produce in terms of trigonometric function cos omega mt into cos omega ct. When applying trigonometric solution, we will be getting either cos of omega c plus or minus omega m of t. So based on the requirement, we will be selecting either for the upper sideband or the lower sideband. So here you could see at the output case, after solving for using trigonometric solution, we will be just getting either the upper sideband or the lower sideband characteristics. So here there is no carrier, and here you could see one of the sideband, that is upper sideband, is not present, whereas here there is no carrier as well as lower sideband is not present. So here based on the mathematical representation, we have just arrived for the single sideband suppressed carrier AM. Now coming to the power calculation. So we know the power calculation is based on the total power contained in the sidebands. So here we have only the upper sideband or the lower sideband. So we will be calculating with respect to the power contained with respect to the equation we have obtained in the at the last of the single sideband suppressed carrier amplitude modulated wave. So for the case of upper sideband, we will be considering this equation. For the lower sideband case, we will be considering this equation with respect to minus. So what is the power here? Power is nothing but either it will be upper sideband or it will be lower sideband. Now we will see how it is calculated. So we know the standard formula for power of cos signal is in terms of V square by R, that is written in terms of VRMS square, that is voltage is considered in root mean square value. So we are going to consider the root mean square value of this equation. Means here the amplitude part of the signal is nothing but contained as a product of the voltage with respect to message and the carrier by 2. So I am going to substitute here instead of VM, it is AM AC by 2, that is the product what we have obtained here. This is the equation. What is present here is to be substituted in case of voltage. So I am substituting it here and we are getting AM square AC square by 8R. So since we are having only one sideband, we will be calculating it as the same. So whereas in double sideband case, both the sidebands are present, so we will be having here 2 AM square by AC square by 8R, so it gets cancelled, and for that double sideband case it is AC square AM square by 4R, whereas here we are obtaining it as 8R. So the power calculation for this single sideband suppressed carrier is in terms of upper side, either it will be upper sideband or lower sideband will be AM square AC square by 8R. Now coming to the advantages of SSB-SC AM. Here, since only one sideband is present, the bandwidth or spectrum occupied is very less because this is only having FM, whereas in double sideband it will be having both the case of 2 FM. So bandwidth is less. Then transmission of more number of signals is allowed with respect to this case, and power is also saved when we are reducing the sideband. And here high power signals can be transmitted too, and less amount of noise is present and signal fading is less. So noise and interference is much reduced in case of single sideband suppressed carrier. Next, coming to the disadvantages of SSB-SC AM. Here the generation process and reduction process is quite complex because we need to suppress one of the sidebands. Here the upcoming topic will be explaining how this is complex, and the quality of signal gets affected unless the sideband transmitter and receiver have excellent frequency stability, because they have to maintain the frequency stability to select upon the lower sideband and upper sideband, which is exactly the same. Then what are the applications of single sideband suppressed carrier AM is, since it is a power saving requirement is done excellently well. This is applied wherever power saving requirements and lower bandwidth requirements are needed. Also in land, air and maritime mobile communication it is applied, and for point to point communication is also it is applied, and in radio communications, in televisions or telemetry radar communications it is mostly applied, and military communications such as amateur videos where one shot of signal is to be sent. This kind of SSB-SC AM signals are applied, right? Now coming to the generation and detector part. So here generator and detector part we have basically two methods. One is frequency discrimination method and the second one is phase discrimination method. So under a frequency discrimination method we will be studying about the filter method, and phase discrimination has two types. One is phase shift method and another one is the modified phase shift method. And the demodulation part is same like double sideband suppressed carrier AM, which involves a coherent detector. We will see one by one. So first one is the frequency discrimination method. In this method, we will be first generating a double sideband suppressed carrier AM with the help of a product modulator, as the mathematical equation also shown the same. Then this double sideband suppressed carrier AM wave is applied as an input to the filter, which reduces or suppresses the unwanted signals, and this band pass filter produces the output which will be the exact of the single sideband suppressed carrier AM what is required. So here it will be selecting the frequency range of band pass filter as the spectrum of the desired SSB wave is required. So hence it is selecting its own frequency range. This frequency discrimination method is also called as selective frequency method. It is also called as selective frequency technique or selective frequency method. So the other name for frequency discrimination is nothing but selective frequency method. So this means that the bandpass filter can be tuned to either the upper sideband frequency or the lower sideband frequency to get the respective single sideband wave which is having only one of the sidebands. So this is the block diagram which is used for frequency discrimination method or selective filtering method. So generally it can be simplified as a as a product modulator, which is nothing but a DSP SE modulator which is given to a band pass filter. That is what explained in the previous one. So band pass filter, here this DSB-SC AM generates with respect to the message as well as the local generated carrier oscillator which gives the signal of a carrier signal and produces the output of a double sideband output. Then it is filtered to give an SSB output. So this is what explained previously. This is expanded into versions where this dotted lines acts as a band DSP-SC AM signal. So this is the message signal which is generated. So it can be an audio amplified output which is given here as well as from a crystal oscillator buffered condition, and a case of a frequency which is required is given to the balanced modulator. So this balanced modulator produces a message signal and gives the input to the single sideband suppress filter, that is USB. Then it is given to the balanced mixer which out of crystal oscillator it produces the single output. So we will see step by step how this is done here. So simply, as I said, the equation based on this will be with respect to the previous derivation part where we have seen in SSB-SC generation, simply multiplying the product of the signal and obtaining this. The same equations can be written for the frequency discrimination method. Hence it generates SSB-SC AM. Now coming to the phase shift method. It's a very important university question as far as this phase shift method is considered. It is asked repeatedly. So here you will be having two modulators. That is, let us consider this as a modulator 1 and this as modulator number 2. So here you could see the message signal is directly fed to one of the modulator and carrier is phase shifted and sent to the modulator, whereas for the second case the message signal is phase shifted by 90° and given as input to the second modulator, and here you could see for the local oscillator a 90° phase shift is again provided to the modulator 2. So the first case of the modulator has the carrier C of t as well as the message M of t without any phase shift. For the next case, it will be having a phase shifter. Here's example, here the message signal will be phase shifted, means example if M of t is given as sin omega mt, it will be having sin omega mt plus a phase shift of 90°. That is what is involved. Here also carrier will be phase shifted, means sin omega ct plus a 90° phase shift is provided. So this is fed as input to the second case of the modulator, and here this will be producing an output. Example, this is the output of S1 of t, means just a product case, that is message signal M of t into carrier signal C of t, whereas here also this case S2 of t will be this case of M. Let us take this as M1 and this as C1. Here it will be M2 of t and C2 of t. What is C2 of t is phase shifted version, as well as the message is also a phase shifted version. Now we'll derive the same case, how it is obtained for the same. So this is theoretically explained here. We'll see the consideration for modulator 1. So for modulator 1 case, we'll be having Vc of t as case 1, it is directly given. So it is Vc example sin omega ct, and here it is Vm of t, means it is Vm sin omega mt since it is directly given, whereas this is for modulator 1 case. Next is it is for modulator second one. Here we'll be having a phase shift, that is Vc of t, I am taking it as Vc sin omega CT plus a phase shift of 90 degree is given. Whereas in message signal, Vm of t is taken as Vc into sine omega Ct plus a 90 degree phase shift is given. So here this can be also written as, so we know by trigonometric solution this equation can also be written as, what is sine omega t plus 90 degree phase shift is nothing but in terms of cos, it is cos omega ct. What about this here? It is Vm, right? It will be Vm cos omega mt. So here for the second case we are considering the message as Vm cos omega mt and Vc cos omega ct, whereas the first case it is sine and sine term only, because here with respect to phase shift it is converted into cosine signal. So what is the output of modulator 1? Modulator 1 output is nothing but we are getting it as, in with respect to diagram, it is S1 of t I suppose. So it is nothing but Vm of t into Vc of t, just a product of the same. It will be Vc sin omega Ct into Vm sin omega mt. For here the output of modulator 2 will be S2 of t, which is nothing but this case, right? Vc in Vc of t into again Vm of t. Here it will be Vc cos omega Ct into Vm cos omega mt. So now based on the diagram representation, you could see here this is your S1 of t and this is your S2 of t, till that we have obtained. Now what this signal is fed to where? To the adder. So this is given to the adder, just you have to add the signal. We get S1 of t and S2 of t is summed together to produce S2 of t. So at the final stage what we are going to do here to get the output of SSB-SC AM is nothing but just add these two signals, this signal and this signal is added. So what will be the added signal here is, here S of t is nothing but S1 of t plus S2 of t, which is nothing but Vc sin omega Ct into Vm sin omega mt plus Vc cos omega Ct into Vm cos omega mt. This, by using a trigonometric solution, this can be rewritten as, this is nothing but in terms of trigonometric solution sin A sin B cos A cos B formula. So here what is sin A sin B and cos A cos B formula? It is nothing but sine of A plus B. We can write this as in terms of sine means it will be cos. It will be in terms of either it will be cos of A plus B or cos of A minus B. Since we are having all these plus terms, only one sideband is present here. Here A term is nothing but omega c and B term is nothing but omega m. So it is omega c minus omega m into t. So here we have obtained the upper sideband where there is no carrier as well as no sideband. Hence we have generated single sideband output. This is upper sideband output with respect to single sideband suppressed carrier AM generated. Hope you have understood this generation part. Next is about the detector part. So in detector part we'll be seeing the same process of a double sideband suppressed carrier AM technique, which is used for the detection part, which uses a coherence detector. So the process of extracting the original signal from the SSB-SC wave is known as the detection or demodulation of SSB-SC detection part. So coherent detector is used for demodulating of the same. So coherent detection is also called as a synchronous detection because here the carrier signal which is used for generating SSB wave is used to detect the message signal also. Hence this process is called as coherence or synchronous detection. And it is assumed that the local oscillator signal is exactly coherent or synchronized with in both the frequency as well as in the uh, phase time of the carrier signal. Hence, it is called as coherent reduction or synchronous demodulation. So, the same is explained here. With respect to the block, if it is considered, here the message signal can be extracted from the SSB-SC wave just by multiplying it with the carrier signal. So the result is then passed through the low pass filter, and filtered out. After filtering out, we will be getting the desired message signal. So here you could see a product modulator is used for the same. The input what we have generated as the single sideband suppressed carrier wave is fed as an input to the product modulator, and a local oscillator generated carrier signal is passed through it. So just it multiplies to produce the output. So here it will be contained as well as the message as well as with the carrier signal, but what we need at the output is exactly the message signal what we have transmitted. So just by passing it to a low pass filter, it will produce a demodulated output, which is nothing but the message signal. So this is shown in an equation format how it can be obtained. So if I am considering S of t as the signal, that is I am considering either one of the sideband is suppressed. So I am considering a lower sideband means a carrier is generated by means of a local oscillator output. Now this is nothing but taken as a product, the previous case, right? So the output of V of t will be S of t into C of t. So S of t into C of t. So after substituting the corresponding values and solving for the same, we will be obtaining in terms of AM AC square with respect to cos term, which is a product of cos of here also substituting in terms of trigonometric solutions, cos A cos B formula is used, and we are obtaining the same of V of t term in terms of AM AC square by 4 cos of 2 omega mt plus AM AC square into cos of this term, right? So here you could see the two terms are present here, and we want only the message signal, whereas this signal is to be suppressed. So this is the desired equation. So when passing it to the low pass filter, only the first term is obtained. So finally the scaling factor for this term is considered as AC square by 4. So after the scaling factor is applied, we will be obtaining only the Vm cos omega mt term. So this is about the single sideband suppressed carrier demodulation part. So hope you understood about single sideband suppressed carrier AM. The power calculation will be explained in the next video. So you will be better understanding how the power saving is done. Before engaging with vestigial sideband, I will be taking about the power saving in the upcoming session. Thank you.